Welcome back to Lahari tutorial. Okay, now let us discuss about molecular orbital energy level diagram for a homonuclear diatomic molecule. So, according to molecular orbital theory, the nuclei of the two atoms lie at appropriate distance and all the atomic orbitals of one atom overlap with all the atomic orbitals of the other atom, which provided the overlapping orbitals are of the same symmetry and similar energy, and which forms the two molecular orbitals. So when, according to MOT, when the two atomic orbitals are overlapping completely, then there is a formation of a two molecular orbitals. So the one is bonding molecular orbital and another one is a anti-bonding molecular orbital. So here, accordance with the molecular orbital theory, we have to discuss the molecular orbital energy level diagram for a homonuclear diatomic molecule. So we know that homonuclear diatomic molecule, so that is if the two nuclei are the same, for example carbon molecule, nitrogen molecule, oxygen molecule, like this. Okay, it is the homonuclear diatomic molecule. Similarly, heteronuclear diatomic molecule, that is CO, NO. So H2O, HCl. Okay, it is what these are example for a heteronuclear diatomic molecule. So now we are going to discuss about homonuclear diatomic molecule. So the general electronic configuration, that is for the molecules up to N2, that is we know that the nitrogen atomic number, that is the 7. So for a nitrogen molecule it is the 14. So number of electrons less than or equal to 14, we have to use this configuration. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equal to pi 2py, then sigma 2pz, pi star 2px equal to pi star 2py. So in this molecular energy level diagram, it is very important. If we know the energy level, so the configuration, so we can easily draw the energy level diagram. Here this sigma and sigma star are the bonding molecular orbital and it is a anti-bonding molecular orbital. Here the atomic orbital, which is the 1s atomic orbital, is overlap with the another 1s atomic orbital. So there is a formation of a two molecular orbital sigma 1s. So here this sigma 1s is a bonding molecular orbital and sigma star 1s is the anti-bonding molecular orbital. Similarly, sigma 2s, sigma star 2s. Here 2s and 2s atomic orbitals are completely overlap and formation of a two molecular orbitals, bonding and anti-bonding molecular orbitals. Similarly, in case of a 2px, 2py and 2pz. Okay, so then for molecules beyond N2 means more than 14 electrons. So we have to use this configuration: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px equal to pi 2py, means both have in a equal energy. So this is configuration is in the increasing order of energy. We know that in a general electronic configuration, the accommodation of electrons is always which follows the three rules. Okay, that is Pauli's exclusion principle, Afo principle and Hund's rule of maximum multiplicity. Here also this configuration which follows the same rule, and this configuration we have to write in a increasing order of energy. So then with the help of this energy level diagram, we can find out the bond order and magnetic property of the molecule. Then what is the bond order? It is defined as half of the difference between the number of electrons in a bonding molecular orbitals and number of electrons in a anti-bonding molecular orbitals. Okay, here half of difference between the number of electrons in a BMO and number of electrons in a ABMO. So after calculating, we'll get the number 1, 2, 3, whatever. So sometimes we may get a 0 also. If we get a 1, it means the two atoms in a molecule is bonded by a single covalent bond. So 2 represents the double and 3 represents the triple bond. Similarly, if it has a 0, so if we get the value, bond order value, so if you get the bond order value 1, it means a single covalent bond. If it get 2, double covalent bond, that is a double bond. If it has 3, then it is indicating a triple bond. If the bond order having the value 0, means the molecule doesn't exist, means we can easily say the molecule doesn't exist. So then another one is we can calculate the magnetic properties. So we know that there are two types, paramagnetic and a diamagnetic property. So we know that a paramagnetic in a orbital. So according to Pauli's exclusion principle, we can accommodate only 2 electrons in a single orbit with a different spin. So if the orbit having a paired electrons, if the orbit having a paired electrons, it is called diamagnetic. And if an orbit having a single electron, so single electron andre unpaired electron, so unpaired electron ittu andre then it is called paramagnetic property. So with the help of molecular energy level diagram, we can come to know the number of bonds present in a molecule and the magnetic properties. Okay, let us consider some example. So consider hydrogen molecule. So hydrogen molecule. So we have to draw the molecular energy level diagram. First, and we know that the electrons present in a hydrogen atom. So for a single hydrogen atom, it is 1 electron. We can write the configuration 1s1. Okay. So similarly, in the another hydrogen atom, it has a 1 electron. The configuration will be 1s1. So the total number of electron present in the hydrogen is 2 electrons. Okay. We have to write the configuration. So general configuration. According to MOT, we know that when the two atomic orbitals are combined together, so there is a formation of two molecular orbitals, sigma 1s, sigma star 1s. Okay. So write sigma 1s, then sigma star 1s. Okay. So we know that the s orbital having a single orbit, we can accommodate 2 electrons. Okay. This is a lower energy. First we have to accommodate in a lower energy orbital, that is a 2. Total number of electron is 2. So now let us draw the energy level diagram. So this is atomic orbital and here it is atomic orbital. So we know that the atomic orbital, 1s atomic orbital, and here it is 1s atomic orbital. Then which forms the 2 molecular orbital. Sigma 1s and sigma star 1s. So here the bonding molecular orbital having a less energy than the atomic orbitals. So here the bonding molecular orbitals having the less energy than the atomic orbital. Similarly, the anti-bonding molecular orbitals having a more energy than the atomic orbital. So for this reason we have to draw the energy like this. Okay, these are atomic orbitals, bonding molecular orbital, and these are a molecular orbital. It is a bonding and it is the anti-bonding molecular orbital. So the bonding molecular orbital having lesser energy than the or lower energy than atomic orbitals, and this anti-bonding molecular orbitals having higher energy than the atomic orbitals. Okay, so this is what the energy level diagram. It is also in the increase, we have to draw in increasing order. Okay, so now we have to accommodate electrons. The one is, see here, the one is having one electron and one is having one electron. Okay, the atomic orbital having one electron here and one electron here. So we have to accommodate in a molecular orbital. That is, first we have to accommodate in a lowest energy. Lowest energy yaudu? Bonding molecular orbital. So the one orbit can have a two electrons with the opposite spin. Okay, now we have to tally this one. The number of electrons present in a atomic orbitals must be equal to the number of electrons present in a bonding molecular orbitals. Okay, here we have a two electrons, then the in a molecular orbitals also we have the two electrons. Okay, now let us calculate the bond order. So we know that a definition, bond order means the half of difference between number of electrons in BMO and a number of electrons in ABMO. Okay, see, the number of electrons in a BMO, bonding molecular orbitals, we have two electrons here, right? So there is no any electron in antibonding, you can consider as a 0. So what you will get? 1. So the bond order 1 means here the two hydrogen atoms are bonded by a single covalent bond and the molecule will be exist. Okay, so now the magnetic property in the molecular orbital. So there is no unpaired electron present in a molecular orbital. So we have to consider only molecular orbital. Just ignore the atomic orbitals. Okay, so in the molecular orbitals we have only paired electrons, means there is no unpaired electrons present in a molecular orbital, so that it has a diamagnetic property. Okay, the hydrogen molecule has a diamagnetic property. Okay, now let us consider another example. Okay, let us consider the carbon molecule, that is C2 molecule. We know that first we have to write the general configuration. For the general configuration we must know the number of electrons present in a carbon atom. In a single carbon we have 6 electrons, right? Similarly the configuration will be 1s2, 2s2, 2p2. Okay, similarly in another carbon it has a 6 electrons. The configuration will be same, 1s2, 2s2, 2p2. So for combining in a carbon molecule, so in the carbon molecule the number of electrons will be 12. 12 electrons. So I have told you that it is less than 14 electrons. So if it has less than 14 electrons, we have to write the configuration. First, the two 1s atomic orbitals are combined together to form a two bonding molecular orbital and anti-bonding. That is the two molecular orbitals. The one is bonding, so another one is a anti-bonding. Okay, similarly this is for 1s. Then 2s, sigma 2s, sigma star 2s. Okay, now when the 2p orbitals are combined, means 2p atomic orbitals are combined together to form a two molecule. When the 2p atomic orbitals are combined together to form a two molecular orbital, that is pi 2px equal to pi 2py. Okay, so the antibonding molecular are pi star 2px equal to pi star 2py. So we have to accommodate electrons here. So in the s orbital we have a 4 electrons. So 2 and here 2, or you can directly accommodate electrons into these molecular orbitals. There are total 12 electrons. Here 2, 2 and here 2, here 2. So now the total electrons are 12. So now let us draw the molecular energy level diagram. Okay, so first we have to take the this is energy level diagram for a carbon molecule. So ಇಲ್ಲಿ ಟೈಮ್ ಜಾಸ್ತಿ ತಗೋತೈತಿ ಅಂತ ನಿಮ್ಗೆ ನಾನು ಆಲ್ರೆಡಿ ಹಾಕಿರೋದನ್ನು ತೋರಿಸ್ತಿದ್ದೀನಿ. ಸಿ ಸ್ಟೂಡೆಂಟ್ಸ್, now we have to accommodate electrons in the molecular orbitals as well as atomic orbitals. Okay, so the first in the configuration we have, in the bonding it has 2 electrons, in a anti-bonding it has a 2. First we have to accommodate a atomic orbitals. Here 2 electrons and here 2 electrons. Now in the bonding molecular orbitals there are 2 electrons. In an anti-bonding it has a 2 electrons. Now in the 2s we have 2 electrons. In the 2s atomic orbitals, total 4 electrons, right? So here 2 and here 2. Okay, then go for the p orbitals. Okay, there are total 4 electrons. Okay, here 2 and in another atomic orbital we have to take the 2 electrons. Now in the bonding and anti-bonding molecular orbitals, first we have to accommodate in a lowest energy. Both these pi 2px and pi 2p having the equal energy, so we have to accommodate here 2 electrons and here 2 electrons. Okay, now we have to count the number of electrons present in anti-bonding molecular orbital must be equal to the number of electrons in a bonding molecular orbitals, including bonding and anti-bonding. Okay, here 2, 4, 6, 8, 10, 12. Okay, in a atomic orbitals we have 12 electrons. So in a molecular orbitals 2, 4, 6, 8, 10, 12. Okay, now let us calculate the bond order. So we know that the bond order Okay, half of difference between number of electron present in bonding molecular orbital. So bonding molecular orbital, we have to count the number of electrons here. 2 plus 2 4 plus 2 6 and plus 2 is 8. Okay, total there are 8 electrons. Then in an antibonding 2 plus 2 4. Okay, it is 4, right? So you can count the number of electrons here also. So these are bonding molecular orbitals, right? 2 4 6 8, right? In an antibonding we have 2 plus 2 4. So now calculate. You will get the bond between the two carbon atoms, that is in a carbon molecule. You will get a 2. So the between the carbon it is bonded by the double bond, right? Next, the magnetic property. So in the molecular orbital there is no unpaired electrons present, so that the molecule is diamagnetic in a character. Okay, the carbon molecule is in a diamagnetic. Okay, hope you understand the concept, the molecular energy level diagram for a homonuclear diatomic molecule. So if you want more example, please comment. Thank you.